We're going for a quick review of related rates. I'm going to bring you through three scenarios. My triangle's a little cluttered and small, so maybe you would sketch it out larger. But what I have here is a triangle with most sides labeled with a variable, a number, and a calculus variable. A variable, a number, and a calculus variable or symbol. Let's start off with the most basic. In this case, this is the one we're going to do first. That's our most basic example. And as I look at this dx dt, positive 3, tells me this triangle is getting a longer x value. The dy dt is negative 2, which tells me this piece is getting shorter. So what's really happening is this thing is morphing towards something that would look more like this. It's a gradual metamorphosis, like a butterfly. So if I want to find dh dt, I look at all this stuff and I say, hey, what's a good equation from my math past that seems to represent this scenario? And sure enough, the Pythagorean theorem shows up again. Once I have my equation from my math past, I take the derivative with respect to time, and if things are going well, everything in here has a substitute or a value I can get from up here, except for the one thing I'm looking for. And we were looking for dh dt, and that's what we need to find. Now, I'm not going to go through the steps because this is supposed to be a warp speed review, but you would need to do the math and then move this thing over here by division to get dh dt. But you would then find the rate at which that hypotenuse is changing. All right, let's look at the next example, finding d theta dt. If you look at this triangle, as it morphs to this triangle, that angle is going to change. Well, what we're going to have to do is use a trig function instead of the Pythagorean theorem to get at that angle. Now, there is very frequently more than one trig function that can work in the scenario. I chose tangent, but that's not to say that you couldn't use sine or cosine. Tangent, according to your geometry upbringing, is opposite over adjacent, y over x. So I take this equation from my math past, and I take its derivative with respect to time, just like I did over here, except this derivative is uglier. We've got quotient rule with this part, and the derivative of tangent is secant squared. Notice, though, that all these little symbols must be honored. If you skip any of those little symbols, you'll end up wrong. Nobody wants that. Once you're to here, you should be able to grab information from the triangle and plug it in and solve for d theta dt. I did a little bit of trickery here though. See this secant squared? That's technically like 1 over cosine. If I have a 1 over cosine squared on the left, I multiply by cosine squared and multiply by cosine squared to cancel that out and move it over here. So this thing on the left becomes this thing on the right. It's a little tricky. And here's one of the things that really gets people. You're so used to the unit circle that when you're looking for a cosine substitute, you start thinking about the unit circle values. But the unit circle only works for specific locations around the unit circle, famous locations like 2 pi over 3. Since we don't have that here, this cosine, which turns out to be 15/17, I go back to my geometry days where I said cosine is adjacent over hypotenuse. Cosine is adjacent over hypotenuse. Cosine is adjacent over hypotenuse. Since it's squared, this times that. So by the time I do all that number crunching, I get the radius, or the theta is changing by, I better add a negative. It's decreasing by 0.187 radians per second. Put a negative there just in case the police are watching. All right, let's look at the final one. As this triangle is morphing, the area within the triangle is also changing. So, what would I do about that? At what rate is the area of the triangle changing? I reach into my math past and I find a formula that seems accurate for the situation. It's this, although some people would like 1/2 base times height. We all know they're the same. You choose whatever form you want. And just like we've done in the other problems, we're going to take the derivative and then we're going to plug in information. Before I took that derivative though, I decided to multiply each side by 2. I don't know why, you didn't have to. I just thought maybe it would make my derivative calculations easier. And instead of using base times height, I went to x's and y's because that's what I was using in the original example. And now if you follow this piece, the derivative of the left, product rule, derivative of the right, and once I take all this mess and start plugging in values from the triangle, I'll be able to solve for dA dt and I'll get my final answer. And I'm just going to make one up here. Let's just pretend it's 7. It's not going to be 7, I'll guarantee you that. If I needed to come up with units, the numerator unit would be area, the denominator unit would be time. So I'll just make this up because we didn't have units. I'd say meters squared per second. Leibniz symbolism and units always go hand in hand. That's it, but it was longer than I wanted.